Alrighty, let's move on to this last little bit with the differential equations. We're going to do some terminology, and then we got just one example, and then we'll get into this. We'll wrap up kind of this video and this topic. All right, here we go. If y is directly proportional to t, then we could write this little equation. That means y is equal to k times t. And then there, k, that's just for some constant value k. So for some constant k. And that k is, you could think about it as being the constant of proportionality. Like, for instance, 50 is proportional to 5. And it would be 10 times 5. So the k value would be 10. Or how like 56 would be proportional to 8. Because it's a scale factor of 7. Right? So if two things are related via multiplication, you could express them as having that directly proportional, aka proportional. Okay, so this word directly isn't really necessary. They could say directly proportional, or they could just say proportional, but those mean the relationship between those two things is via multiplication, right? So y is equal to k times t. If something is inversely proportional, well, what's the inverse of multiplication? Oh, that's right, it's going to be division. So here we could write it as y equals k divided by t. Make sure you divide by the variable, right? It's this divide equals to k, and you divide by the other thing. You don't divide by the constant, because that's really just multiplying by the reciprocal. You need to divide by the variable part. So if two things are related via multiplication, you could call them proportional. Oops, nope, I didn't want to do that. Oh gosh, okay, let's fix it. So wonderful. Thank you, Smartboard. Here's what I wanted to do. I wanted that, and then that. Yep, okay. Let's see. I think, did I lose anything? That looks okay. Y equals kt. There's proportional, and then inversely proportional. The inverse of multiplication is going to be your division. All right, very good. So if something is jointly proportional, that just means it's proportional, or you could say it's directly proportional to both. Again, the word directly isn't really necessary. If it's there, that's great. But if it's not, it's understood to be there. So you could say, hey, y is jointly proportional, or you could say, hey, y is directly proportional to both x and 5 minus x. That means it's related to both via multiplication. So here I could just write y is equal to k times x times 5 minus x. You don't need k times k. You don't need a k squared. You just need that one constant. So proportional means multiplication. Inverse proportional means inverse of multiplication. That means division. And then jointly proportional means it's just directly proportional to both. Okay, so let's look at these couple of examples, and then we'll get into the example 2 at the bottom. It says write a differential equation to represent the following. Part A, a certain population P increases at a rate proportional to time T. Now here's the really common mistake. You see P equals KT, and you're like, okay, Mr. Bell, there it is, but that's not even answering what the question wanted you to do. The question wanted a differential equation. It didn't want just an equation. And a differential equation has to have a derivative in it. So it's not P equals, right? It wasn't P that was proportional to T. It was the rate of P, right? It says a certain population increases at a rate. And it was the rate that was proportional to t. So here we're going to write dp dt, right? The derivative. If you want to do p prime, that's the same, but it's the rate of change of p, aka the first derivative, dp dt. That's the thing that was proportional. So dp dt equals to kt. All right, next one's going to be similar. So our population p increases at a rate. Again, it's the rate of p, and that's going to be proportional to the square root of the population. So dp dt, that's the rate of p, directly proportional to k times square root. And so the square root of the population, so the square root of p. Part C, let p represent the number of bears. Now, whether they have p of t or whether they just have p, like it's the same. It's like writing f of x versus just writing f, right? It doesn't really matter. You don't have to put the independent variable defined with those little parentheses. You can if you want to, but you don't need to. So let P represent the number of bears in a population at time T years. Time is greater than or equal to 0. Population P is increasing. Again, it's the rate of P, and that's directly proportional to 800 minus P. So here the rate of P, dP dt, is going to be directly proportional, so K times, and then it was 800 minus P. Alrighty, and then part D says a certain population Y increases the rate. Ooh, so now it's the rate of Y. So the rate of Y is, and that's new. It's inversely proportional to this other thing. So the rate of Y, dy dt, it's going to be inversely proportional. So it's going to be K divided by, and then here we had the 250 minus Y. So directly proportional means they're related via multiplication. If they're jointly proportional, that means it's just directly proportional to both. So everything's multiplication. And if it's inversely proportional, that means the relationship is via division. Okay, so we've got to know the terminology, because sometimes we will need to just read the verbal description, and then we'll have to kind of come up with the differential equation ourselves. But let's look at this example. We'll do it, and then this video will be over. It's a pretty quick video. Okay, here we go. It says the rate at which a puppy gains weight is proportional to the difference between its adult weight and its current weight. At time equals 0 when the puppy is first weighed, its weight is 3 pounds. A piece of T is the weight of the puppy in pounds. And T is the time days after its first weighed. Then, and it gives us the differential equation, dP dt equals 1/5 75 minus P. Let Y equals piece of T be the solution to the differential equation with the initial condition, piece of 0 equals 3. Use separation of variables. I love it when it tells me exactly what to do. Use separation of variables to find Y equals P, right? So we're going to integrate to get from that derivative up to the original function. Starts me with the differential equation P prime, wants me to get up to what P is equal to. Okay, so separate, integrate, use the condition to solve for C, finish the algebra, or at some point in that algebra, use the condition to solve for C. And then you just got to get it to P equals. Let's kind of go through the verbal description of this, and let's kind of like color code everything, and let's see what it really gave us. It says the rate at which a puppy gains weight. So again, it's the rate at which it gains weight. So the rate of the weight. So there you go. There's your dP dt. Remember, P is the weight. So the rate of the gaining weight, that's going to be your dP dt. And then it says is proportional to, so there's the K times, notice your K value here was 1/5, so it's K times, so 1/5 times, and then it says the difference between, so that's subtraction, right? Difference means subtraction, and it says difference between the adult weight, here, I guess the adult weight of that breed of dog is 75, and then its current weight, remember the current weight was P. So the rate, that's the red part, dP dt, the rate of the weight is proportional to K times the difference between 75 minus the current weight, which is 75, and then P. So like, just based on this, if it would have told me the K value, and if it would have told me that the adult weight is 75, if it would have told me those two facts, then it wouldn't have had to give me the differential equation, because it gave me the verbal description, and then I could then take those words and then I could translate them into the math. But we like it when it gives us the math. That's nice. But sometimes, as we'll see in the next video, sometimes it's not going to give us the differential equation. So we'll have to create it ourselves. But here it gives it to us, so that's really nice. Okay, so here we go. Let's jump into it. We got, come on. We've got dP dt is equal to 1/5, and then we had 75 minus P. We got to separate these variables. So that means the chunk with P's is going to need to move over to the other side, because it's going to have to be with the dP. And that means the dt is going to have to kick back over. So let's go ahead and separate these variables. 75 minus P is going to need to divide over. Going to have 1 over 75 minus P dP, and then kick the dt over also, So that's 1/5 dt. Okay, so I've separated the variables. That's good. Remember, your general process for all of these kind of differential equations, the first thing is to separate. Right, separate the variables. Get all the x's and the dx on one side. Get all the y's and the dy on the other side. Or here we have p's and t's. We've got to separate first. Right, separate the variables, and then we would integrate. Right, there's the calculus step. Integrate, separate, integrate, and then 3 and 4. They kind of go together. Really, 3 is within 4. 3 is you're going to use the condition to solve for the c value, and then 4 is just finish whatever algebra you need to get the y equals, right? To get y equals or p equals or whatever. And at some point in that process, remember, if this was like 10 steps, right? You have the first step, then you go down to the 10th step. It's a really terrible one. At any point in that process, you could then solve for c, right? You can solve for c at the beginning, then do the 10 steps, or you can solve for it in the middle, like do some of the steps, then solve for it, then finish, or you could do all the steps of algebra, then plug in. It doesn't really matter. But at some point in that algebra, you need to use your condition to solve for c and then plug it in, right? So really that step 3 happens within the step 4. Right, we have all that algebra to finish. At some point in there, separate and then solve, or separate. Separate first. At some point in the algebra, we're gonna use the condition to solve for the c value. Okay, so that part's done, right? We have separated. Now we need to integrate. So here we're gonna go from this step to the next. We're gonna integrate. Now the right side is just gonna be 1/5 t, and we'll put the plus c on that side. On the left, we need to do a little bit of a u sub. We're going to set the u as equal to 75 minus p. That means the du, the derivative of 75 is 0, but the derivative of negative p would be -1. Kick the dp over. So your u sub was supposed to have a negative, right? You were supposed to have a negative right here. Since that negative is supposed to be there, but it's not, it just means my u sub would be off by that -1 constant. So this is what the integral would look like if we were to switch it over to being in terms of u, which we know will be negative ln of u. And then so here we go, I'm going to go ahead and just jump, right? The integration of 1 over 75 minus p, it's going to be negative, don't forget the negative, ln 75 minus p. Really, it was this negative inside that ended up kicking out that negative outside because of the u sub. So don't forget that negative on the outside. Alrighty, so now the next step would be actually we're going to move that negative over, and then we're going to exponentiate. So I'll have 75 minus p is equal to c e negative 1/5 t. Then I'm going to come up here and I'm going to look at that initial condition. I'm going to think, hey, is that value, right, that p value, is that a positive or a negative? Here I can see clearly that it's a positive. So what's really nice is that when I have that positive term, I'm going to come pick this up here. When I have the positive term, I do not need to worry about the absolute value. I can just drop those suckers, and then I don't need to do anything else. So I've got 75 minus p, that's going to be equal to c e to the negative 1/5 t. If you wanted to finish the algebra, you could, or you could solve for c right now. Typically, you would want to deal with the natural log and then deal with the absolute value, and then you could solve for the c. Or you could finish more algebra. It doesn't really matter. I'm just going to finish the algebra. So let's get the p by itself. Basically, these two things just going to swap, right? You're going to add the p over, then you're going to subtract the exponential. So those just trade. So I'm going to get that p. Actually, I'm going to erase that and make it a little bit bigger. We've got the p value, and I'm going to write p. You can change it to p of t if you want. P is going to be equal to 75 minus c e to the negative 1/5 t. Oh, I forgot our steps, didn't I? We integrated. I was like way back here. We've actually finished the algebra now also. So now all that's left is to just use that condition and solve for the C value. So let's go for it. We knew P of 0 was 3, so 3 is going to be equal to 75 minus C e to the 0. E to the 0 is 1. And C times 1 is C, so here we go. We've got that 3 is going to be equal to 75 minus C. You don't really need that because times 1 doesn't change anything. And so I know just by looking at it, or if you want to add the C over and then subtract 3, we know the C value is going to end up being 72. And then take that C value and then plug it back in. We're going to get this particular solution. The function for the puppy's weight, as determined by time, is going to end up being 75 minus 72 e to the negative 1/5 t. And we would have that same domain restriction, so it would be only from time is greater than or equal to 0. But that would end up being our answer. That is the differential, that's the equation. That's the equation that would have this as the derivative and is also going to go through that point as the y-intercept. Okay, so our kind of general process, we finished that. Our general process for all the stuff we saw last time, or today, depending on when you're watching this video. And then also for what we're going to see next time, in the next maybe 2.5 times. Whenever we have these differential equations, it's always these same steps. Separate, integrate, solve for the C value at some point in the algebra, and then finish all the rest of the algebra to get it to y equals. That's how we do these. Now, everything we've seen up to this point, excluding this example, has been just no context, just straight up math. Here's the differential, here's the point, here's the condition. Go forth and do it. But what we're going to see as we move on to these applications in the next video, and then in real life in the next class period and a half or so, is we're going to see these differential equations buried in the context of a word problem. Sometimes the word problem will give us the differential equation, like it did for us here. It gave us that, so it was really nice. Other times it will only give us the verbal description. We'll have to create it ourselves, but the math is going to be the same. Separate, integrate, finish the algebra to get to y equals, or to get to p equals, or to get to whatever equals, and then at some point in that algebra, use the condition to solve for C. All right, that's the whole idea with these differential equations. We'll pick back up with the next video with some of the applications, the word problem ones, but we're done right here for this one.